Hello, George Notchik here. This video, rather than being the final video on the barrel test for the curvature of the Earth, is just going to be another update. I had intended this to be the results video, but I had a lot of difficulties in getting everything done, and by the time everything was ready and went out on the ice, the sun was getting to the point where it was at right angles to the line of sight to the barrels, which means it wasn't illuminating the barrels the way that I intended, and it was just too difficult to pick out the background, the barrels in the background. There just wasn't enough contrast, unfortunately. I could see it with my eyes in looking through the auto level and the theodolite, but I couldn't capture it on camera. I just don't have a good enough setup to image on in a video what you're seeing through a theodolite or a auto level. I need to work on that. I don't know if I can improve it much beyond what I have, but it isn't as good as viewing through the eye. I was able to make observations with the eye, but I couldn't capture it for you on camera, so we're going to have to wait for another day. I was hoping today would be the day. I woke up early to get out on the ice, and clouds had rolled in. It was very flat light, but to really make it difficult, it was drizzling. So there's the air was at 100% humidity with water droplets, so that just ruined everything. So hopefully within the next few days I'll be able to get some good video on what happens in viewing the barrels from a distance at varying heights above the ice and at various distances from the barrel. But we can't do it quite yet. I'm not quite there. So what this video is, I'm going to give you a little more information here at the beginning, and then it'll follow up with a trip I took out to the out on the ice at 6 miles. Con and I went to Home Island to inspect the 6-mile target that I had left up. We also made some measurements out there on the ice, and then there's footage of the trip out and back from Home Island out at 6 miles. So for those of you that are interested, you can watch that. But for those of you that are only interested in results, we're not there yet. You can stop watching, or watch now for the next 10 minutes of some of the results that I got regarding some interesting measurements, and then after that, if you don't want to watch the rest of the video, you don't have to do that. It's not going to give you any information regarding the curvature. So to get started here, what I have is temperature data that I took. What I use for measuring temperature is this thermistor array. There are 5 thermistors mounted on this pole, 1, 2, 3, 4, and 5, and they're separated by 30 centimeters and 30 centimeters to the base. So when this is placed on the ice, we're measuring a temperature profile, vertical profile, every 30 centimeters, starting 30 centimeters above the ice. And then you can add another pole to this and align the base up where the last thermistor was and get another 5 sample points in the vertical above the ice, or above whatever you want to measure. And that's what we have here. I did 2 sets of 5. Here's the ice surface. The pole is placed down on the ground like this. This is our pole. So it's sitting down on the ice. 30 centimeters above is our first thermistor, and then every 30 centimeters. Then we mount the thermistor pole on another pole and raise it up. So the thermistor pole is sitting here, and then it's on an extension, and we have another 5 points. So by doing this, taking 10 measurement points in the vertical above the ice, we get a total of 3 meters. 10 points at 30 centimeters is 300 centimeters, or 3 meters, which is 10 feet. Basically, 300 millimeters is real close to 12 inches, and that would be 30 centimeters, is approximately 12 inches. So each one of these thermistors is separated by about a foot. Now, so we have 10 points. I started in the morning. This is when I got through getting everything ready at the barrels. It was almost noon when I took off, and before I took off out onto the ice, I made this profile measurement back at the barrels. Here are the coordinates at 48.61510 degrees north by 93.30812 degrees west at 1110 feet above sea level. Barometric pressure was 30.25, and this is the temperature profile of the air corridor. And interesting is the air temperature was heating up at this point. The sun was out, and we can see how unstable things were getting at this point in time. At about 1 foot above the ice at 30 centimeters, I was reading 2.88 degrees centigrade, and the highest reading I got was almost 6 degrees centigrade, almost a 3-degree temperature change here, going from the first foot to 5 feet up. And then it was varying because the wind was blowing. We weren't getting real good mixing because the sun had come out and it was really heating the air fast. It had been cloudy up until about this point, and the air was fairly stable, but now it was changing rapidly. And here's a set of data when I returned back from being out on the ice at 2:54 p.m., almost 3 p.m. And we can see that there's still some instability. It had warmed up considerably. We'd almost warmed up by 4 degrees centigrade during that time period of 3 hours. But it was starting to get a little more stable, but there's still quite a bit of variation. Now, here is the data of the temperature profile made at 6 miles out on the ice, away from the barrels. And I made my first measurement at 12:24 p.m. Here are the coordinates out on the ice. You'll see it in the video where I parked the truck there, and where I had the corner reflector for measuring the ice height. That was at 48.64284 degrees north at 93.18726 degrees west, also at 1110 feet elevation. Barometric pressure hadn't changed much, fairly stable actually, from 32.5 to 32.9. So the barometric pressure over the ice was fairly uniform. And here we can see again we're having a fair amount of variation. Not as much as what I had back at the barrels, but there's still quite a bit of instability in the air at this point. And then I made another set of measurements when I was finished and about ready to head back home. an hour later, and here is the air temperature profile. We see that we're on average it increased a bit, around 2 degrees over the prior hour, but we see that there's a lot of instability in the air there, and I was seeing that. I've seen a lot of shimmer looking through the auto level and the TopCon total station. Now what I did is, even though I couldn't capture it in the video with my eye, I made these measurements using the TopCon total station. I could make out the structure. I was up on a hill, up off the ice, on a hill by the base of my 6 mile target, and this, by measuring with the total station that you'll see, was about 18 feet up above the ice. So it was 18 feet above the ice. I could see the whole structure from the base on up to the top of the 20-foot pole. And I could make out the banding in the different colored barrels as I had intended. Now, I took the TopCon total station, and there you have, it's a crosshairs that looks something like this, and I took this portion of the crosshair and lined it up with a point on the structure. The first point I lined this center up with was the top of the 20-foot pole, and I measured the vertical angle as being 90 degrees, 5 minutes, 35 seconds. Then I adjusted so that the crosshairs was at the top of the barrels, and I measured it at 90 degrees, 6 minutes, and 10 seconds. Remember that the amount of pipe that's sticking above the barrels is about 5 feet. Each barrel is 3 feet. That gives us 15 feet to the top of the barrels, and then we have two 10-foot sections of the sewer pipe. So a total of 20 feet. So what's left over, the protruding amount, is 5 feet. Then I also measured to the bottom of the first set of barrels, and I got 90 degrees, 6 seconds, or 6 minutes and 45 seconds. But it's blurry and pretty hazy. It was kind of hard to get it lined up exactly. But those are the measurements. Now let's look at the angular difference here. The angular difference between 90 degrees, 6 minutes and 10 seconds from 90 degrees, 5 minutes and 35 seconds, the way we do that is the 90 subtract out, so we have 6 minutes, 10 seconds, and we're subtracting from it 5 minutes, 35 seconds. Since this number is larger than this number, what we do is we borrow 60 seconds from this side, we make that 5, so this becomes 70 seconds, we subtract 35 seconds from it, and we get 35 seconds. So the angular difference here is 35 seconds. And we can see that the angular difference here comes out to about 35 seconds. Well, because it was blurry and hazy, that's accounting for the difference here. Is if 35 seconds gives us a 5 foot, for a 5 foot height difference, we should have a little bit lower here with this only being 3 feet. But like I said, it was kind of hard to set up, so this really isn't a really good measurement. But this measurement I can fairly well trust. Well, how much is 35 seconds of arc? This is about 1/2 the resolution of the eye. The human eye has a resolution of 72 arc seconds. So with the equipment we can do better than the human eye. This is the human eye resolution is twice of what I measured with the TopCon total station. Well, let's kind of look at the numbers here and see what we have. Okay, in order to relate angular resolution to actual physical height measurements, we use the relationship that the distance that we're trying to measure, or the length that's subtended by some angle, that is, theta is the angular measurement on some physical height d, or physical length. And if we know the distance from observation out to that physical length that we're trying to measure, the relationship is that d equals r theta. That's just simple geometry. Now, theta in this case has to be in radian measure. It cannot be in degrees. It needs to be in radian measure. And d and r have the same units of measurement. Well, to convert between degrees and radians, and say we're measuring the angle in arc seconds, and we want to get theta in radians, what we do is we take theta in arc seconds, divide by 3600. There's 3600 arc seconds in a degree. Then multiply by pi and divide by 180. And that comes out to 4.848 microradians per 1 arc second. So each arc second is 4.848 microradians, or 4.848 times 10 to the minus 6 radians. Well, what does this translate to? Well, if r is a distance of 1 mile, then d, putting into this equation, let me rewrite that. Let's get back here a second. D then is r times theta in radians. Well, this would be theta in arc seconds times 4.848 times 10 to the minus 6. This is the relationship. So if we know the distance r from the observer to the length we're trying to measure, d, and the angular measure is given in arc seconds, then d will be just the distance out, r, times the angular measure in arc seconds multiplied by that factor. Well, 1 arc second, if we put in here 1 arc second, then corresponds to a length measurement d of 0.0256 feet in a mile, where r is 1 mile. And this is 0.307 inches in a mile. So if you can resolve 1 arc second, and the distance out that you're measuring is a mile, the length that you can resolve through an angular measure of 1 arc second is 0.307 inches in that mile, which is about a little more than 1/4 of an inch. You'd be looking at probably about 3/8 of an inch. Now, the resolution of my TopCon total station is 5 arc seconds. So what does this relate to? Well, it's 5 times this number. Well, 5 arc seconds then tells me I can resolve at a mile a length of 0.182 feet in a mile. 0.0125 is 1/4 or 1/8, so this is about 1/8 of a foot in a mile that I can resolve with the Topcon total station, or multiplying this by 12 to get how many inches. We get 1.536 inches in a mile. So my total station, my theodolite, has the capability of resolving a distance, a length measurement in a mile of 1.536 inches. Now, how about over 6 miles? Well, it would be 6 times this number, or about 9 inches. 1.5 times 6 gives you a little bit, gives you 9 inches. So, over a 6 mile distance, the uncertainty that I would be measuring in a height is about 9 inches. In measuring a length measurement using the theodolite. 1.536 times 6 give me 36, 18, 21, 32. So that would be 9.216 inches. That's my uncertainty in 6 miles using my theodolite. Now, on the trip out on the ice with Con in the truck, I've turned the audio off because there's a lot of noise due to the roughness of the ice and the wind blowing in through the windows, because I need to keep the windows open in case the truck went through the ice so that we could easily escape. So there'll be a few minutes of silence and just video. Measurement and observation. Con decided to come along, but ever so reluctantly. He's really nervous. Got the windows down, which is the standard procedure when going out on the ice. Is you want to have your windows down in case you go through the ice. You want to be able to get out of the vehicle, and if your windows are up, you'll be locked inside by the hydrostatic pressure pushing against the doors. So you want your windows open. It's an island. We're just passing the channel marker. We're at 2.72 miles from home and headed out to Home Island, which is 6 miles away. So halfway out where I had the 4 mile marker last year. There's a reef there. We're still in American waters, about a mile away from the Canadian waters. We'll enter Canada. The ice is a bit rough. I'm able to maintain a good 30 miles an hour, steady 30 miles an hour. Just noticed I had the camera on the wrong setting, so we're getting a little overexposed. Here we are. There's my 6 mile target. It doesn't look too bad. Tape's coming off a little bit on the top. Home is back that way. We get a tripod set up so that the camera's steady, and then start looking back that way. Now we're going to get set up here, get our coordinates. We're at 48.64, 284 degrees north by 93.1 8728 degrees west at 1105 feet elevation. Got a corner reflector for measuring ice height. I have a reference up by the target that we know when Jesse Kozlowski was here the exact height, so I can measure take the theodolite up there and shoot it down to the corner reflector and get the exact height of the ice. There's our coordinates. You can see them good. I'm now up by the target. You can see it up in the tree there. 2x4 that it's mounted on here, up on the hill. And what I'm going to do now is measure the horizontal and vertical distance to the corner reflector that's down on the ice, so I can get the exact height of the ice. The viewing conditions aren't very good. The sun has swung around to the south, and it's not hitting the target very well. So it's really difficult to see. I'm going to have to do the target shooting tomorrow. I'm now up by the target. You can see it up in the tree there. 2x4 that it's mounted on here, up on the hill. And what I'm going to do now is measure the horizontal and vertical distance to the corner reflector that's down on the ice, so I can get the exact height of the ice. The viewing conditions aren't very good. The sun has swung around to the south, and it's not hitting the target very well. So it's really difficult to see. I'm going to have to do the target shooting tomorrow. It's getting too late in the day now. It's Friends and Island right there. Getting shimmer on the ice because it's heating up. But right now, you can see that I'm shooting the corner reflector. And we'll make a measurement now. I can see with my naked eye, I can see the barrels and the 4-inch 20-foot pole, but the camera just can't get a sharp enough image. I'm going to have to work on that and for a camera mount on the theodolite. But here I'm going to go ahead and make a measurement. You can see that it's measuring. There, that's the hypotenuse of a right triangle. And we'll step through. That's the horizontal distance out to the corner reflector. And that's the vertical distance. So we're 18 feet above the corner reflector out on the ice. Again, there's the hypotenuse of the triangle, the base, and the height. I'll do one more measurement. Again, there's the height, there's the hypotenuse, and there's the base. So now we have that measurement. Now I'll measure the theodolite height reference to my reference mark that I established last year. Just take a quick look around here from the height. It is so nice and peaceful, quiet. There's a town of International Falls, it's a paper mill. Here's the theodolite setup. Record some data too. Wonder what happened to Con. He went out exploring somewhere around here. He loves it out here on this island. He loves to explore. Last year I caught him exploring and found him a mile away on another island. Yeah, back to work. I now have the total station aimed at the corner reflector that's mounted at the reference point on the tree that's holding the 6-mile target. You can see their corner reflector there. Now I'm going to shoot distance. Just swing the theodolite around from when I measured the position to the corner reflector on the ice. And now we'll go ahead and make a measurement with the total station here. So there's the hypotenuse. There's the base, the horizontal distance to the corner reflector. There's the vertical distance. We'll do one more measurement. That's the hypotenuse. There's the base. And there's the height. Here I'm making the air temperature measurement with the thermistor array. You can see the thermistors. There's 1, 2, 3, 4, 5 thermistors. They're 30 centimeters apart. Now I'm going to sample the air temperature here. Ready to head back home. I'm going to leave the tripod for the theodolite and auto level set up, so we'll be ready in the morning when we come back. But before we head back, I'm going to play with Con for a bit. He's been a really good boy, real patient. So come on, Con, get your stick. Well, Con decided he wants to run. So I'm ready to go, Con. Let's go. Gonna let Con lead the way. That's just the seatbelt buzzer going off. I'm not wearing seatbelts when I'm on the ice. Last thing you want to do is go through and try to figure out how to take your seatbelt off. Again, we're coming upon the portion of the video where I've turned the audio off because of the noise going across the ice, and there's just video for a few minutes without any sound. Step it up here, Con. Let's go. All right. Doing about 20 miles an hour right now. Come on, Con, let's go. Good boy. Sit here and wait for him to catch up. There he comes. Getting windy again. Good boy. Come on. Good boy. Out in the middle of the bay. Certainly looks flat, doesn't it? It's looking west towards home. Falls. The Boise Paper Solution, or now Packaging Corporation of America, owns the paper mill. Back from where we came. There's the target on Home Island. Well, we are in Canadian waters. No, we're out of Canadian waters now. We're a mile in on the US side of the lake. Well, Con, shall we head home now? Okay. We're here on Franzen Island. There's an interesting marker on the island. Let's see, there's Conway down on the ice. Yeah, there he is. About a half-mile away. So he's run 3 miles so far. We'll see if he wants to get into the truck on the return trip home. He just might want to run the other 3 miles. He loves to run. Should be a sled dog. This is the channel marker on Franzen Island. Kind of rugged. This is called schist, this rock. It's denser than granite. Here's that marker. It's a geodetic marker. And here's another. Alright, here comes Con. I'll walk over here on the island. There's a spot that I use for Equinox viewing. It's a really great spot. There's a really flat ledge for mounting equipment on. Oh man, a lot of dead wood in the woods here. This island's really good midsummer. Has a lot of blueberries on it. Yeah, here we are. Got a really nice ledge, flat, for mounting the equipment. Another place over there that's flat. And then a little bit of mound here. This is fairly flat. If you look due east, the sun on the equinox will sit right over there on the horizon. So it's a really nice view for equinox viewing. finding rock reefs for summer loading to know exactly where we're at. That will have about 2 feet of water above it, which is just perfect for taking out the lower unit of the boat if you happen to run in that spot. Come on! Where are ya? Come on! Come on, boy! There he is. Good boy. He's looking for something to drink. Go get him some water. In lack of water, he'll eat the snow. Go ahead, get your drink. Yeah, there's a channel marker. A little tuckered out, aren't you, Con, huh? Yeah, let's see if Con will get in the truck this time. Ready to go, Con? Come on. Come on. Get in. You gonna run some more? Shall we go run? Come on. We're gonna go run. You gonna go? You gonna ride? Huh? Come on. You gonna get up? You wanna run some more, huh? Okay. On the last approach to home, we're about 7/10 of a mile. Con finally decided to get in at about a mile from home. He ran 5 miles, but he sure enjoyed it. He loves running on the ice. We didn't do much snowmobiling this year, so I guess he's making up for lost time. I've got to kind of negotiate this. Well, there's the target. Con and I just finished dinner. It's around 7:30 in the evening. and just doing an overview before I shut down for the night. There's the barrels. Back up here a bit. You can see the structure. Hopefully it'll last through the night. I have it guyed down good and secure. And if we look out this way, that's our test range, the optical corridor down a little bit past Franzen Island. You can see the Franzen Island channel marker there at the end of the island, and if we pan there in the center of the screen, that little white dot, that's our 6-mile target that showed you earlier in the video that I installed last year. Now, something that has me concerned, I was listening to the weather report for tomorrow, and there's a possibility it's not going to drop below freezing tonight. And that means the surface ice is going to get real soft, and also there'll be puddles of water around that will put a lot of moisture in the air. So I'm certainly hoping we drop below freezing tonight so we can get a good start in the morning. Unfortunately, I wasn't able to take care of this the last 2 days. It just too many logistical problems in getting set up, and I'm all set up now. And if we have a good day tomorrow, then we'll be able to make observations and measurements. Certainly hoping that happens. But this is the nature of things, is sometimes things don't work out for you. Mother Nature doesn't cooperate. And you just have to make allowances. If I don't get it this year, well, just wait until next winter. But hopefully I'll be able to get this concluded tomorrow and then leave it up in case we have a few other good days in the next week. But I'm not going to be able to keep it on the ice here for more than a week. I know it's in these holes here, this slush area. The water was pumping earlier, and it drilled a hole through the ice. So that tells me the water is starting to move underneath the ice, and tends to pump up and down when it does that. It mixes the water underneath the ice and starts melting the ice from below. So you can't really tell how thick the ice is, because we get more significant melting underneath the ice than we do on top this time of year. So anyway, that's it for now. I was hoping that this video would have more data and observations, but it's the best we can do at the moment. Like that water, Con? Good fresh water. Well, let's go to the house, Con. Time to wrap it up for tonight.